Hey there, chemists. In this lesson, we're going to keep looking at some properties of complex ions, specifically their shapes, and then some reason why they form interesting colors. So to start us off, I have two examples of what are called geometric isomers of a platinum complex. The one on the left is called cisplatin, and the one on the right is called transplatin. These are both square planar complexes with two ammonias and two chlorine ligands, but hopefully you can see that they're not the same. These are different. They're called geometric isomers, which means the ligands have a different spatial orientation. The left one is particularly interesting. It happens to be an anti-cancer drug. That's due to the chlorines falling off the platinum. The platinum forms a bridge with guanine bases in a strand of DNA that prevents cancerous DNA from unzipping and replicating, and that's a good thing when it comes to treating cancer. It's one of the earliest chemotherapies developed in the 1970s. The notation cis refers to two identical ligands, in this case, let's say the two chlorines, and that they are 90 degrees apart from each other. Likewise, the two ammonias are 90 degrees apart from each other. But when they're on opposite sides and 180 degrees apart, that's called a trans isomer. So these have different properties, particularly different chemical properties, but they're very similar. And the only way to distinguish them is with the name or with actually drawing them out. And it's highlighted over here, but make a note for yourself. This only applies to square planar and octahedral complexes. We do not see geometric isomerism with linear or tetrahedral complexes. That does not occur, but you do see it for square planars and octahedrals. Okay, the rest of this lesson is about the colors that transition metal compounds form, and it all has to do with their d electrons. Remember from last semester, we were able to draw what are called orbital diagrams for any atom or ion, and transition metals have these 5d orbitals. So if we wanted to look at an orbital diagram for the iron cation, go look at a periodic table and start with just iron itself. Using the noble gas shorthand notation, it would be bracket argon, the noble gas that you pass along the way to hitting iron, followed by 4s2 and 3d6. Now, what about when we form the 3 plus ion? Well, remember, transition metals lose the s electrons first. So Fe3 plus is still going to have the core argon notation, no more 4s2, and then you lose one of the 3d electrons, which means it has 3d5 in its configuration. That means I can put one electron in each of these 5d orbitals. And this is what a free floating gas phase iron 3 plus ion looks like. But what about when we see it in solution or in a complex ion? Well, when you form a complex with ligands, the orbitals are no longer degenerate. They actually exist in different energies. This is just one example of what it looks like for an octahedral complex. There are others. But the main point is that they are no longer at the same energy level. So there's one way I could arrange my 5 electrons, filling the lower energy level first and then having nothing up above. So then what about this explains why we have all these colors for the various compounds? Well, from this what's called low spin state, which is given that name because there are fewer unpaired electrons, we can add energy, and this can absorb light, just in the form of visible light, and excite one or more of these electrons to what we call a high spin state. Here we've excited 2 of them to the empty orbitals up above, and you get a situation with more unpaired electrons. And that's it. It's just that energy gap between these two, which has the ability to absorb visible light, and we end up seeing what's not absorbed. They give the notation delta to describe this energy gap. It's called the crystal field splitting energy. And it actually depends on what the ligand is, what the geometry is, what the metal is, what charge it's forming. There's a lot of different numerical values that you get for this energy based on that, and that's why we see so many different colors. All that's important to know for this class at this level is that that energy gap exists, and visible light is enough to excite an electron from a low spin state to a high spin state. So how do we turn an energy into a color? This actually makes us go back to last semester once again and use this equation, which relates energy to wavelength. Wavelength is proportional or is related to what visible color we see. So let's talk about one example of a titanium complex. There's an octahedral hexa-aqua titanium 3 ion, and let's say it takes 3.9 times 10 to the negative 19 joules to excite its d electron between the spin states. To get the wavelength of energy, to get the wavelength of light, we're going to rearrange this equation from E equals hc over lambda and write lambda equals hc over E. H is Planck's constant, 6.626 times 10 to the negative 34 joule seconds. C is just 3 times 10 to the 8th meters per second, and E is 3.9 times 10 to the negative 19 joules. So joules cancel with joules, seconds cancel with per seconds. We'll get a numerical value of 5.10 times 10 to the negative 7 meters. That's perfectly fine, but most of the time wavelengths are reported in nanometers. So go ahead and multiply that by 10 to the 9 to give nanometers, you get 510 nanometers. So what color is this? Well, you have to go to a chart, either that's listed or showing the colors, and just find where 510 exists. That's in the greens, maybe the blue greens. So how do we know what color is absorbed and what's observed? Well, this is the energy of light that's absorbed. So we are absorbing green light. And if I go over to this color wheel in the upper left, you draw an arrow right through the middle from where you absorb the light, and what comes out on the other side is what's observed or emitted. So the absorbed color is green, but the observed color based on that color wheel would be red-violet. So that's just a overview of some of the properties we observe about complex ions related to the fact that they're usually transition metals at the center. Their colors come from the energy gap between these non-degenerate d orbitals, which all transition metals have, and they can exist in different shapes than we've ever seen before via geometric isomerism. Thanks for watching.